In this video, we're going to be introducing some mathematical concepts that are going to be useful tools for us as we continue to analyze oscillating or vibrating systems and electrical systems that also vibrate and oscillate. Specifically, we're going to be talking about complex numbers. So in the past, what we've seen is that the imaginary number I is equal to the square root of -1. Um, Now that we're dealing with electrical circuits and current, which is also I, the complex number, the imaginary number, is usually referred to as J. So square root of -1 is J. Um, and so J is an imaginary number, and we can express complex numbers, which are some combination of a real part and some imaginary part. So A plus bj equal to z is a vector that exists on the real imaginary plane. Or if you have A here and B there, you have that vector that is A plus B times J. Well, remember that Euler's formula, e to the I theta, is equal to cosine of theta plus I sine of theta. And if you kind of squint at it, you can see that cosine of theta is a real component, or A, and I sine of theta is some imaginary component, B times J. I'm switching between I's and J's, apologize. So A plus BJ, cosine theta plus I sine theta. And if we look at some triangle or a vector with an angle theta, if the magnitude of this vector is 1, then we have a cosine theta down here and a sine theta right there. So cosine theta plus j times sine theta is a vector representation of an imaginary number or a complex number that has the angle theta in this real imaginary plane. And so another way that we can represent z equals a plus b times j is what's called a magnitude phase form. Z equals some magnitude times e to the j times the phase of z, or an angle. So I'll call this Cartesian, a Cartesian form, where you're just dealing with the axes, and this is magnitude phase form. And you can see, you might be able to see that a plus bj forms a triangle, is a vector that forms a triangle, and magnitude phase form is another way of looking at that triangle, where the magnitude of z is equal to the square root of a squared plus b squared. And the phase of z, so that's just kind of a picture of an angle. Phase of z is equal to a tan 2 of b and a, or an arctangent of b and a. And so just a little bit about the math of complex numbers. So z1 is equal to z2 if a1 equals a2 and b1 equals b2. So if they have the same imaginary and real component, they're equal. Imaginary numbers will have a complex conjugate. And the complex conjugate of z equals a plus bj, also written as z times e to the j times a phase. The complex conjugate of that number is a minus bj, which is equal to the magnitude of z times e to the minus j times a phase. If you draw this on the real complex plane, the complex conjugate of z1 of z is right there, and we usually denote that by a z star. So it's just mirrored across that imaginary axis. If you want to add or subtract, then z1 plus z2 equals a1 plus a2 plus b1 plus b2 times j. So that's similar to a vector, it's a vector addition. You add the elements together, and that's the same with subtraction. You can also multiply or divide a complex numbers by a real number. So some real number r times z is equal to r times a plus r times b j. And if we look at, we can also multiply in magnitude phase form. If we can show that graphically. So if z is right here, then 2z is going to be over there. Similarly, minus z is over here, and minus 2z is over there. You're moving along a straight line. And so if we write this out in magnitude phase form, r times z is equal to the magnitude of r times z times e, and it's going to be the same angle, j times the phase of z. And that's if r is greater than 0, or greater than or equal to 0. If r is less than 0, then you're going to have magnitude r times z times e to the minus, or no, not minus, sorry, j times the phase of z plus or minus pi. If r is less than 0, that means you flipped it 180 degrees. We can also multiply two complex numbers. So if we have z1 times z2, that's going to equal a1 a2 minus b1 b2, and that's all a real component, plus a1 b2 plus b1 a2 j. So that's an imaginary component. Makes a little more sense to look at it in a in magnitude phase form. So if we write this in magnitude phase form, it's the magnitude of z1 times the magnitude of z2 times an exponential, and then we have the phase of z1 plus the phase of z2 times j. So we multiply the magnitudes, add the phases, and that's how we multiply two vectors together, two complex numbers together. We'll go ahead through a few examples of exponentiation of complex numbers. So we can raise z to some exponent a. And there's a few examples given here in the book. Let me go ahead and add a picture of these rules. Okay. So we have a few different possible combinations. So if we have a positive base, or a positive real base with a real exponent, that is r to the a. So let's just go ahead. Let's just skip to some examples here. So if we have like the example given in the book is 1 to the 1/4 power. So that's going to be a positive real base with a real exponent. So r is 1 and a is the 1/4. So that equals 1 to the 1/4, which is 1, times e to the 2, and a was 1/4, times some constant, so times n, times pi, j. So that's going to equal, so 1 to the 1/4 is 1, times e to the 2/4, so that's 1/2, pi over 2 times n times j. And we go pi over 2 kind of around the circle until we increase n to take pi over 2 around the circle until we start seeing repeats. And so what this ends up giving us is plus or minus 1 and plus or minus I. Because if n equals 1, then pi over 2 times the angle pi over 2 is a straight up and down vector. So I to the 1/4 is also going to be a solution for the 4th root of 1. And I won't go through examples of the rest of these, but these rules for exponentiation, we'll get more practice in the homework for these. We'll go ahead and end there.